This is a depiction of the Michelson Interferometer. Here it is not in motion. When it's in motion, it's static on the Earth, and the Earth is considered to be moving through the so-called ether. And the Michelson-Morley experiment was to determine whether or not there was an isotropy in the speed of light. In other words, the speed of light was affected by the direction of motion of the Earth through this so-called ether. But what happens is a beam of light comes in, hits this beam splitter, half goes vertical, and the other half goes straight through, reflected off the mirror, comes back, reflects off the back of the mirror, of the beam splitter, and this reflected radiation goes through the beam splitter, and the two beams mix at this particular point on the detector. This could be an eyeball or a film. In the old days, that's what it was. Nowadays, it could be an electronic detection apparatus. So we'll begin to talk about this one a little bit more later. But first, I want to talk to something that's related to this particular system. And that's what's called a photon clock or a light clock, which consists of a pair of parallel mirrors separated by a distance d, and a light pulse or a beam of light is reflected back and forth between these two mirrors, and the round trip time for a single pulse of light would be 2d over c, and that's in a stationary configuration where there's no motion, or so putatively no motion. What happens is that when the system is in motion, now either this system can be in motion or the observer can be in motion relative to this system as a static system, and that will basically determine which direction this apparent beam of light will go. What happens is that when the observer is in motion in this direction versus the apparatus moving in that direction, what you get is an apparent path of the light. If you were to put smoke in here and observe where the beam of light is, the beam of light would seem to follow this kind of diagonal path. And the way it is analyzed is that the light following these paths is considered to be moving at the speed of light, c. However, what happens is that the speed of light is, because light is inertial, is non-inertial, it continues to bounce back and forth. And what happens is the apparatus moves relative to the beam bouncing back and forth and gives a diagonal path, apparent diagonal path, or if the observer is moving, this again is, as we saw in the prior video, the apparent motion then is also given by this kind of diagonal path. What they have done, though, is they've attributed the apparent beam of light along this diagonal path is moving with the speed c, when in fact it's moving with the speed c prime. The pulse of light is continually bouncing perpendicular between these two, regardless of whether the apparatus is moving or regardless of whether or not the observer is moving. It just is which direction these diagonals go. But the false assumption is that the beam of light along the diagonals is moving at the speed of light c, and it's not. You can show that in fact if the light is bouncing back and forth between these mirrors with the speed c, that this apparent speed, c prime I call it, is actually greater than the speed of light. And what they've done in all their analyses is, by ignoring the fact that this is a non-inertial propagation of radiation, they falsely attributed the motion of light at speed c to be along these diagonals. So that's the basic issue that we're dealing with. Now, if we go back and take another look at the Michelson Interferometer and look at it with the same perspective of who's moving and in what direction, what you find out is that the way it is basically diagrammed is that when the apparatus is moving in this direction, which would be when it's in a laboratory on Earth and it's moving with the Earth, and the Earth is moving in this particular direction relative to the orientation of the interferometer, this is the path of the light. And actually, if this apparatus is moving in this direction, and this is not the proper path, it just simply can't move in that direction. It would be in the opposite direction, as we saw from the prior. The appearance would be the other way. So by doing it this way, what they're doing is attributing a inertial component to the light in the direction of propagation or motion of the interferometer, which is totally wrong and also backwards with respect to what they're actually observing. So what's really happening is this: the light comes in. If the apparatus is moving in this direction, then the light goes up and lags behind the motion and comes back to this location on the detector. What happens here with the horizontal beam of light is that it comes down and it also is reflected off of this thing, but it has no component of velocity, and therefore the apparatus continues to move away from the light, which would normally come down vertically, but in fact is displaced, or apparently displaced, because of the motion of the apparatus in this direction. Now you can change the perspective. You could say, well, okay, the apparatus stays still. You have an observer who's moving with the apparatus and he sees one thing or measures one thing, and you have an observer who's moving in another direction horizontally relative to the apparatus, and this is what he sees, and you compare what one sees or the other sees. And again, this business of who sees what or who measures what, you wind up with these terms of who sees what, and you've got to be awfully careful. As we saw before, inertial motion in the vertical can be made to look, when you measure it, like non-inertial motion. If you take a look at the way I showed it in the prior video. So what you really have is this: the light comes in. If the apparatus is moving off in this direction, I'm a stationary observer, and this apparatus is moving horizontally with respect to me. What happens is the light comes in, hits this mirror, and goes vertical. And this dotted line here is actually, if I were to have smoke in this apparatus, this is where the light would appear to be traveling. And then again, when it reflects off of that and comes down, it would appear to be traveling along the dotted line. Whereas in fact, what it is, it's moving vertically, continually, and we're looking at as if this were a steady beam. There's a different way of looking at this if this were a pulse, as opposed to the way the original experiments were conducted using what was continuous sources of radiation. And this is where we get into an issue of what is the apparatus actually seeing and what is it actually measuring. The reason for that is that the light has to have certain properties if there's to be any interference measured here when the light from both of these two directions reaches this detector or apparatus or film or electronic imaging device, whatever you happen to be using. And that's called its coherence length. And the coherence length has to do with the purity of the color, how narrow the color spectrum is in the light. And natural sources have a very, very broad spectrum. Even though they're very bright lines in certain atomic systems, like mercury gives a bright light, blue line, sodium gives a bright yellow line. Even though these are very sharp and bright lines, they have a very wide bandwidth. And so the interference occurs when the effective path length in the horizontal and the vertical directions are almost identical in length. Causes what's called a phase change, but that's not important. The difference between the paths and the two legs of the apparatus have to be remarkably tight, close together. Whereas if you were to use a laser has remarkably pure light, very narrow bandwidth, and so the length of these two arms and what's happening in these two lines can be vastly different, and you still get enough of this thing called coherence where they mix and give well-defined fringes. Now, the basic issue as I see it in the measurements that have occurred prior to the modern era is that with the detection of fringes is an analog process, and it's very difficult to get very precise measurements. Certainly in the old days when they were using film, these measurements were not very good. In the modern day, I would say we know how to use pulses, and if you want to use pulses, we can get much, much higher resolution using pulses to make our measurements and contrast these. However, if you look at this type of apparatus, what happens is if you've got a regular type of light beam, you must have the place where these two mix, the two arms have to be extraordinarily precise in terms of their relationship, because the very slightest displacement of one pulse, this would be a pulse coming here, and this would be a pulse here, any slight displacement of those two using normal types of systems, even laser systems, you almost can't measure it. The precision is exquisite that you need to have in order for these two pulses coming from the two different arms of the apparatus to mix to give fringes that you can see. So there are some serious problems associated with the use of the Michelson Interferometer, especially if you don't understand that the propagation of light is non-inertial. And you can see the same issue here exists, is that the diagonal paths are apparent paths, and the light is not moving at the speed of c along those paths. It is only moving at the speed of c in either the vertical or horizontal directions. And the speed along these dotted paths is simply not given as c. And that's where one of the fundamental differences is in terms of modeling these types of systems and what they're measuring, and why you get apparent time dilation, because there is a difference. If you take a look at the thing, here's what the time dilation, this is a multiplication, c is greater than that. And so these terms are consistent when you're measuring time of flight or round trip times, but they're using the wrong one. So everything about the Michelson Interferometer is basically mismodeled. You can't trust anything that's being done with the Michelson Interferometer in the past or even in the present. The model is simply incorrect. It doesn't match the physics of the propagation of light.